So I have up here, consider the differential equation dy dx is equal to x minus y. And the slope field is provided. We don't need it, but it's kind of nice to look at. And we're going to let y be some particular solution of the differential equation. So y is like the original function that satisfies the initial condition f of 0, which is equal to 2. And so we don't know exactly what the original function is. But we can estimate what that original function is by looking at the slope field and kind of just drawing it as best we can. So I'm looking at this one. It says to sketch a graph of f on the slope field, and then we're going to use your graph to approximate, and it says f of 1. I'm actually going to change it to make it closer to 0 for what I want us to see. I'm going to change it to f of 0.25, and we'll see why in a second, but that is what I'm going to change it to for the notes. And so first step, we can go ahead and like draw in that approximation. Like, what does that graph look like? Well, if it's going through 0, 2, I know this is a point on the graph. And I can use that point in the slope field to kind of estimate what the graph looks like. What kind of shape will we make if we're trying to draw on this graph? It's a little curve, right? Like we can see it, again, just kind of following it gently. We're just estimating it. It looks something like that. Yours might look a little bit different, but that should be the general shape of it. And we can use that graph to basically estimate something on the original function. So remember that blue one is not the original function, it's just the one that we're estimating of what it looks like. So if I want to estimate what f of, again, 0.25 is, I can go into my graph, so 0.25 will be here, and I can kind of estimate it somewhere right here. So I might say something like it's about, I don't know, 1.5, 1.6. We're just estimating. But that's one way that we can do estimation. Like we can use the slope field, draw in that slope field, and just kind of like pick out where that y value is. What might be a downfall to kind of just using what you draw it to find like an estimation? It will look different. Like everyone's going to draw something slightly different. Everyone's going to find a slightly different estimation. We know in math we often like, and one of the reasons why I like math, like it's always going to be exact. We can get down to some number, we know what it is. We don't have to worry about this time like, oh, I drew a curve and this looks about where it's at. So what we have actually in math to do like a better estimation is going to be called a tangent line estimation. If you actually tried all of homework 1, you probably ran into a problem like this. But a tangent line approximation basically is, we may not know what the function looks like. So there's my purple curve, that could be the function. But if we know the slope and a point, you are able to find a tangent line. Like we know how to do that. And basically, mathematically, if we're doing an estimation, as long as we stay in the region close to that point of tangency, the tangent line and the graph are about the same thing. Like they're close enough for an estimation. So you can kind of see like pretty close to estimate it. The further away you get from that point of intersection, the less accurate it's going to be. There's lots of different types of approximations we have in the field of math. For a calculus AB student, the only estimation we need to know is going to be the tangent line approximation. And it's pretty easy to find. Step 1, you're going to write the tangent line. And we know the tangent line is y minus y1, which is equal to m times x minus x1. M we know is going to come from the derivative, and for most of these problems we will know what the derivative is because it is just going to be dy dx. And then once you write that tangent line, you're going to plug the x coordinate into the tangent. Again, why we can do this is we're saying basically a tangent line is not the graph, but it can be close enough in order to find a good estimation. So let's go ahead and find the tangent line for this one. So I'm going to have y minus the y coordinate is equal to the slope times x minus the x coordinate. It gave us the initial condition. The initial condition y is 2 when x is 0. How do I find that slope? That slope is going to come from dy dx, which is what we can see at the top of the page. dy dx is x minus y. So if dy dx is x minus y, then the slope would be the x coordinate minus the y coordinate, which in this case is just -2. So that would be my tangent line. I like simplifying it before I do an approximation, so I'm going to distribute that -2 across. Of course, that's just a 0, but I have -2x plus 2, and that is your tangent line. And you can kind of visually see what that looks like. So it's going to look something like this on the slope field. And you can kind of see the tangent line is not exactly on the graph, but it's pretty darn close. So we can use that tangent line to estimate what the actual graph is doing. Now you can see when I changed what I originally put in the notes, like f of 1 would not be a good one to use because we start getting pretty far away from where the tangent lines go. So how would I estimate it? We're trying to find f of 0.25. And f of 0.25 is basically, hey, just plug 0.25 into your tangent line. And you can leave your answer like that. It does simplify somewhat nicely. 0.25 is, of course, 1/4. So basically -1/2 plus 2, or 1.5. And again, what we're basically saying is like, clearly we can kind of see in the graph, like, oh, it makes sense we're close to 1.5. But that's just going to be a way for us to standardize kind of the estimations that we find. Find the tangent line, and then find the x coordinate that you're using to estimate it, and kind of estimate it using the tangent line. Tangent lines for these problems do tend to be easier to write because you don't have to find the first derivative. The dy dx is the first derivative. And then in math, we know that when we have an approximation, it's sometimes nice to know if you're going to be over or under the actual value. And how can we tell? We are going to kind of look at the concavity of the graph. I forgot to erase this when I sent it out to you, but hey, there it is. The graph is going to give an underestimate if the curve is concave up. I think that would make sense. That would be because the tangent line is under the curve. So the estimation from a tangent would be below the graph. If your curve is concave down, then your tangent line would be over the graph. So it would end up being an overestimation of the actual value on the graph. So we have like, here's the estimation. That would be the unknown actual value that you are estimating. That kind of concludes the first section of the notes. We have like the slope fields, just finding the derivative, finding these approximations. And then what I did want to go ahead and start today, what I think a lot of students prefer over this kind of stuff, is just the straight up like, let's solve the differential equations. It's very much a like step-by-step process. It's very like algebra heavy, very just like know the integral rules. And I just know students like having like set steps, like do these steps and then get to the answer. So the notes we're going to go ahead and jump to is going to be the one of solving separable differential equations. And when we say solving a differential equation, the answer to a differential equation is a function, not like a number. So it's going to be like the original function. We're not going to do all of these notes today. That's not my intent. But I do know that there are some integral rules that we should review because we are solving a derivative. So we do want to make sure we kind of know our integration rules. Now, if you do need to go back and review your integral rules, you probably want to go back and look at your Unit 5 and Unit 6 briefcase binders, because that's when we did kind of cover all of our rules. I think some of these are pretty straightforward. Like if I say what's the integral of x with respect to dx, what's going to be that integral? 1/2 of x squared. Don't forget the plus c. We could also do the same thing in terms of y. What's the integral of y with respect to dy? 1/2 of y squared plus c. What if we are integrating just dx? What is that going to become? X. Like what number is technically between the integral sign and dx? 1. A 1. What's the integral of 1? X. Don't forget the plus c. What about the integral of y? What is this integral going to be? Y plus c. And then I just try to pick some rules that are common in these types of problems, / ones that I find students sometimes forget. What is the integral of 1 over x? Natural log of not just x, but absolute value of x plus c. Looking at that y1 next to it, what type of rule is that one actually? It is arc sine, so again, looking at the degrees, it's more than 1, so we know it has to be inverse trig. Which one is in that format? It is arc sine. So we can see the a value is 3. Arc sine doesn't have the coefficient in front, so it'll become the arc sine of y over 3 plus c. Some of you might be like, all right, I definitely need to go back and review some of those rules. What about the integral of tangent? This is the one I don't think anyone has gotten the first try so far today. So anyone remember the integral of tangent? There's a negative in it. Negative natural log. Cosine, what's around the cosine? Absolute value plus c. Again, there's lots of trig rules. Definitely go back and review those. And then an easy one, what's going to be the integral of y dy? E to the y. The integral of e to the y is just e to the y. So again, when you are solving differential equations, clearly we're going from the derivative to the original function. There is going to be a lot of integrating. So you do need to know those integral rules. And that includes like all the integration methods. So like u sub's a big one that people forget. It's coming back. So all those integration rules we need to know. So what is a separable differential equation? Besides being the only type of equation you need to know how to solve in this unit, it is going to be one that's written in a certain way. So a separable differential equation is going to be a differential equation that can be written in the form and I'm going to write it as g of y dy is equal to f of x dx, which I think makes it look a little more complicated than it actually is. You can kind of see by its name, a separable differential equation is going to be one where we can separate the variables. And what do I mean by separate? You're going to get all of the y's on one side and all of the x's on the other side. And that's always going to be the first step to these problems today. Like you're going to separate, 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 and then do the calculus part. In fact, on the AP exam, if you have a pre-response question that is a differential equation, and you don't separate your variables, the AP grader just moves on to the next student. Like they don't look at that question anymore. There's no way you can earn any points. They're moving on to the next one. So you do want to make sure you can kind of separate your stuff. So the example of how we would separate, we're not going to really solve it quite yet. But I have dy dx is equal to 2x over 5y squared. Now that dy dx represents the derivative. So often we don't separate them except for this one instance. How do we separate them? You want to like multiply by something on both sides, or you want to divide by something on both sides, or cross multiply, or add something. Like you just need to do some algebra to separate them. I think this one's pretty easy to see. If you cross multiply, you're going to end up with 5y squared dy is equal to 2x dx. That would be a separable differential equation because we weren't able to separate it to get y's on one side and x's on the other. It doesn't matter which side you get each variable. I will say personally, and how you will often see on AP exam, y's go on the left-hand side of the equal sign and x's go on the right. One other thing that you'll see, and many of you will not like this about this unit, is that there's often multiple ways to do a problem because there's going to be a lot of different choices you can make that are all mathematically sound, but all end up giving you the same answer at the end. For example, I could have chosen to separate this one differently. Maybe I just multiplied by the y squared and then just multiplied by the dx. And so you could have separated it this way. And what I just wrote down in purple is the same thing in green, like it would eventually give you the same answer. Personally, I would do the green one because I'm avoiding fractions, but they would both be correct and valid. But the first step you always want to do is separate your variables. So I just have a few examples. I'm not going to work till like the end of the bell, so I want to do at least 2 examples today, maybe a third, and we will see kind of where that puts us. So let's go ahead and look at example number 1. And it says, find the general solution to this differential equation. Now, the instructions for these problems will tell you how much work you have to do. This instruction is actually going to be the least amount of work, because when we see general solution, that's just asking you basically to find the original equation or the original function. If I can spell. And plus c is basically going to be in your answer. You wouldn't have to solve for c, you wouldn't have to solve for y, you just need to get to something representing the original graph. First step to these problems, always, always, always separate. Is this one going to be one that we can pretty easily separate our variables? Yep, we can just cross multiply. So I would have 3y squared is equal to 4x plus 3 times dx. And then I think most of you can figure out what happens next. If this is the differential equation representing the derivative, we've separated and we're trying to get to the original function. Well, how would you go from the derivative to the original function? The dy just disappeared. I'm just so excited to do the next step, I guess. So yes, the 3y is definitely still there. 3y squared dy. Now we can do the exciting part. How would I go from the derivative to the original function? We integrate. And that's why we have the dy and dx there. We're going to take the integral of both sides. Because it is an equation, what I do to one side, I have to do to the other, and then we just integrate each side separately. What are we going to end up on the left-hand side? That's going to become y cubed. What do we need to remember? Plus c. I'm going to call it c sub 1 for just right now. We'll kind of go back to it in a second. And then on the other side, that's going to become an x squared, 4 divided by 2 is 2, plus 3x. Then don't forget my constant. I am going to call it c2. So I integrated both sides. That's why we wanted to separate the variables. I will say I will never ever write my step like that again. I'm never going to use 2 constants. The reason why, when we say plus c, what is that representing? A constant, specifically, do we know what constant that is? No, it is just some unknown number. So mathematically, you're like, okay, well, let me just move this constant to the other side. Well, if c2 is some constant, c1 is another constant, what's some random number minus another random number?
0.
It's not 0, it's just another number, right? So we have y cubed is equal to, and we're just going to write it as 2x squared plus 3x, and that's where I'm going to use the single c. That would be my final answer, and I can stop there at that point because it just asks for a general solution. From now on, I'm never going to do that step in red. I'm always going to jump straight from this line to that line. We only need 1 plus c. And traditionally, we're just going to put the plus c on the side with the x's. You could put it on the side with the y, and again, it wouldn't be wrong. I might be annoyed, so I'll have to like make a different answer for your problem. But the plus c is typically on the side with the x's. And then after the general solution, so that would be, we're done. That would be the final answer. Questions on that? All right, let's try another one. Find the general solution, y equals f of x of the differential equation y prime, which is equal to 1 over 6y squared. How are the instructions to this problem different from example 1? There's the y prime. So again, when we see that y prime, what's another way we could write y prime? dy dx. And so I would definitely do that for any of these problems because we are going to have to separate things. What else is different about this question comparing to the first one? That y equals f of x. And that's what I'm emphasizing. This little statement squeezed in actually means a whole lot in math. So again, kind of comparing them, that first one we did just said, hey, solve this differential equation. This one says, solve it, and the general solution is y is equal to f of x. That tiny statement is telling you to do two things. Your final answer is going to have to be in the form of y equals, so you're going to have to solve for y. The second thing, which is function notation, it must also be a function. So you would want to make sure your final answer is in the form of y equals blah, 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 and then all that other stuff is going to have to be a function. So again, I rewrote this one as dy dx is equal to 1 over 6y squared. Are we able to easily separate these variables?
Yeah.
Yes, what can we do to separate the variables? Cross multiply. Sometimes you cross multiply, maybe sometimes just multiply by one thing. So I have 6y squared dy is equal to 1 dx. As a disclaimer again, if you wrote yours as y squared dy is equal to 1/6 of dx, would that technically be wrong? No, you've separated. Would you want to do that one probably? No, like let's avoid the fractions and do the easier one. After you separate, what's always going to be the next step? Integrate. So go ahead and like, if you don't know what to do this unit, separate and then integrate something. Separate and then integrate. So we have this 6y squared, so it's going to become y cubed. 6 divided by 3 is 2. Again, you only need 1 plus c. I like putting it on the side with the x's. The integral of 1 is x, but don't forget that plus c. If this question asks for just the general solution without that y equals f of x, you could stop right there. It didn't. It did ask for y equals f of x, so we do need to solve it for y. So at this point, it's just algebra. What would we do next? Divide by 2, and then after dividing by 2, what are you going to do? Take the cubed root. So we have one answer of y is equal to the cubed root of x plus c over 2. And you can leave your answer like that. But one thing we want to be careful with this unit is there's going to be lots of different ways to write equivalent answers. For example, I could have also just written my answer like this, and I think this one's obvious, just divide both things by 2. That means the same thing. Here's where it can get kind of weird. Another equivalent answer. What is C again representing?
Just a number.
Just a number. Do we know what it is? No. So if we have some unknown number divided by 2, what is that going to give you? Just another number. I'm not going to call it C. I'm going to pick a different letter. Let's just go down the alphabet. D, it could be anything. But that would be the same answer as the first one. They look different. They also look similar, but those would be 100% correct and equally correct, because those are general solutions to that original differential equation. Questions on that? 3 o'clock. Let's do one more, and then I promise I'll stop after this one. Let's do a particular solution, and we want to kind of wrap up on. For a particular solution, let's compare that to a general solution. A particular solution means that we are going to have to solve for C. So when I read the instructions, again, the instructions tell you a whole lot. So we're finding a particular solution, so we're going to have to use the initial condition, solve for C. The second part tells you what your answer needs to look like. It needs to be in the form of y equals some function. So just by saying that statement, we're solving for C, and our final answer is going to be in the form of y equals. It gives us the initial condition, and so we can just go ahead and start. What's the first step always going to be for these problems? Separate, and the second step is always going to be integrate. So go ahead, separate, then integrate. Cross multiplying works. So I have 3y dy is equal to e to the 4x dx. So I have separated. Now we want to integrate. So find the integral. Again, you only need to have 1 plus c. I prefer on the side with the x's, so does the AP example. That's going to become 3y squared divided by the new exponent of 2 is equal to, what rule do we need to remind ourselves on how to integrate e to the 4x? U sub, right? So the opposite of chain rule. So we do need to do u sub. So we need that quick reminder. U would be equal to 4x. U prime would be equal to 4. So what coefficient is going to go out in front? 1/4. And then the integral of e to the u is just e to the u. Don't forget your plus c's. If it asks for the general solution, you would be done. That's the general solution. It doesn't. It does want us to find a particular solution. We do have a choice. You can solve for y and then plug in the initial condition. Or you can plug in your initial condition first, which is what I prefer, because it tends to be less steps. You just undo a lot of steps if you solve for y first. So at this point, I am going to go ahead and plug in that initial condition, which is f of 0 is equal to -5. So I have 3/2 of -5 squared is equal to 1/4 e to the 4 times 0 plus c. I'm not going to simplify my answer completely, but I'm going to kind of talk about some things. So -5 squared is 25. So now it's going to become 75/2. E to the 0th is 1, so that's just going to be 1/4. So what is c? C is 75/2 minus 1/4. And I know some of you want to simplify that because there's 2 numbers. I'm not, because you're allowed to be lazy, but again, simplify if you want, or leave it kind of separate. Yes?
So, I got it. What did I do? I got 149 over 6. That's 149.
Do you have the same antiderivatives? Yeah. Is there C on the same side as me? You solve for y first, though, that's probably it.
But we're just making sure.
You multiplied by 2/3, so your C became a different C than mine.
Oh, I see.
And that's why you do want to be, like, just, you would want to have relabeled that as a different letter.
Okay. But like, she's not wrong.
No, not your final answer, same as mine. So that's my C. So let's go ahead and plug that C into the problem. So I'm going to go back to this general solution. So I'm going to combine this answer with this answer. And so I would have 3/2 of y squared is equal to 1/4 e to the 4x plus c. I didn't simplify mine, you might have. And now we just need to go ahead and get y by itself. Well, algebraically, what we'll need to do first to get y by itself? Divide by 2/3, which is the same thing as multiply by 2/3, divide by 3/2.
Yeah.
So I'd have y squared is equal to 2/3 times all of this. And then what would I need to do next? Square root. What do I need to remember about taking a square root when solving an equation? Plus or minus. And that is important, of course. So this is my equation, and we want to always check to make sure we have answered the question being asked. We have found a particular solution. This is, the C has been solved for. Is it find a particular solution y equals? We got this in the form y equals. But that function notation tells me that this has to be a function. So are we done, yes or no?
Yes or no?
Guess not, because I'm asking that question, right? Why are we not done? How do I know this is technically not a function? It's the plus or minus. So like it's an ugly square root, but no square roots are like we have the plus and we have the minus. That fails the vertical line test. So right now that's not a function. And we want to go back to that plus or minus and think about what that really means. And it means, hey, it's the plus, or maybe it's the minus, and we need to pick which one it is. It's not going to be difficult. What do we know the initial condition is equal to? -5. So the y has to be a negative. So which one are we going to pick? The minus. So your final answer would be the negative of this. And again, why is that? Like, we know that if we plug in 0 into this, we should get -5. And the only way that's going to happen is if you have a negative on the outside of the root. And many students will jump straight from this step to the last one, and they'll just kind of know which one to pick. Are you going to pick the positive one, or are you going to pick the negative one? And then looking, we have answered the question. We have y equals, we have a function, and we have solved for c. You can see this unit is going to be kind of heavy with the algebra and the steps. The calculus basically ended after that second line. Like, once you found the antiderivative, the calculus is done, and then it's just kind of algebra from there on. So that's where I'm going to stop at today. It's 3:07 to give you some time to work on some assignments. So what you can be working on, we'll finish these notes up tomorrow. But you can go ahead and start working on homeworks 1 and homeworks number 2 now. I will say to shorten homework number 2. The textbook doesn't have you solve for y. My answer key is solve for y. But on homework 2, I'm perfectly fine if you just leave it like ugly. Like, solve for c, but you don't have to worry about solving for y unless you just want to practice the algebra. Technically and officially, you can do all of homework 4 at this point. We've actually learned most of what there's need to know in this unit. The only thing we have to learn, so tomorrow we're going to do some problems that are pretty heavy on some properties of logarithms. And then after spring break, we will do some special types of word problems. Definitely not asking you to do homework over spring break. In fact, I'm asking you not to do any schoolwork over spring break for any of your classes because it's spring break. But that's the homework you're going to be working on now. We'll finish up these notes tomorrow, and then just pick right back up after spring break. Do remember those first 3 days after spring break will be virtual for everyone, so we will have that shortened URL schedule on Monday, Tuesday, and Wednesday after spring break. But y'all can go ahead and get started on that homework. Again, please reach out if you have